Random variables are functions, typically represented by an uppercase letter, whose domain is the sample space and range is a set of real numbers. Random variables can be continuous or discrete. In this video, we will be focusing on continuous random variables. Continuous random variables are variables with possible values along an interval a through b and can be any value between a and b. Possible examples include temperatures, lengths of time, distances measured. Most measurements or measured quantities are continuous variables. Similar to discrete random variables and the probability mass functions we use to describe them, continuous random variables can be described using a probability density function, or PDF, not to be confused with the file type PDF. If x is a continuous random variable, then the PDF of x looks something like this. The probability that x is a value between a and b is equal to the integral of the function of x over the interval a to b. This expression can also be represented graphically, as you can see in the bottom right. The probability that x is a value between a and b is equal to the shaded area under the curve of f of x. The cumulative distribution function, or CDF for cumulative random variables, serves the same function as the CDF for discrete random variables. It gives the probability that the random variable uppercase x is less than or equal to the value represented by lowercase x. To obtain the CDF of a cumulative random variable from the PDF, you must integrate the PDF from negative infinity to the lowercase x value. The CDF, capital F of x, can be used to calculate the probabilities for all possible values of x. And like with discrete random variables, the CDF and PMF, the CDF and the PDF of cumulative random variables can be calculated from each other. You can also use these functions to calculate the expected value, variance, and standard deviation. As you can see, the equation for the expected value looks different from the one used in discrete random variable calculations, but the formulas for variance and standard deviation remain the same. In this video, we will be covering the 4 most common types of probability distributions used when discussing continuous random variables. First, we'll start with the normal and the standard normal distributions. The normal distribution is one of the most common and useful distributions in statistics. This distribution applies to many numerical populations in the world: height, age, test scores, and so on. Even more populations fit an approximate normal distribution. And furthermore, the central limit theorem states that even when a population does not fit the normal distribution, the sums or averages of the population variables will approximate a normal distribution under suitable conditions. So you can see the normal distribution is incredibly important to know and recognize. And the 2 parameters that we use to describe a normal distribution are mu, the population mean, and sigma, the population standard deviation. Most analysis of the normal distribution is done using standardized normal scores. These scores, or z-scores, are calculated using a standard normal distribution, or a normal distribution with a mean mu of 0 and a standard deviation of 1. This distribution is denoted by the random variable z, hence the name z-scores. You can see the PDF of the standard normal variable at the bottom of the screen. The z-scores calculated using the standard normal distribution are used to analyze non-standard normal distributions, represented here by the random variable x, with mean mu and standard deviation sigma. To standardize this variable, you subtract the sample mean from mu, which moves the mean to 0, and divide by the standard deviation, which makes the standard deviation 1, which you'll note are, again, the parameters of the standardized normal distribution. Now, these calculations can be drawn out, so of course we can do the same thing in RStudio. There are 4 basic commands that you'll use to analyze normal distributions in RStudio: rnorm, dnorm, p-norm, and q-norm. First, our norm generates random numbers that follow a normal distribution and takes three inputs: n, the number of numbers you want to generate, mean and standard deviation of those numbers. dnorm gives the PDF for a normally distributed variable with a specified mean and standard deviation, where x, in this case, is the value you want to find in the PDF. pnorm is the CDF function and gives you the area under the standard normal curve for the z-score q with mean and standard deviation as specified. And last, qnorm gives you the z-score for a value p with mean and standard deviation. This function is the inverse of pnorm, where pnorm gives you the probability of a value q occurring, where q is a z-score, and qnorm gives you the z-score for a value p. So instead of calculating out the z-score, you can use the qnorm function to find it. And we'll do a quick demonstration of these demands in our studio, just so you can get an idea of what they look like. We'll start with our norm, which generates random numbers. Let's say we want to generate 100 numbers with a mean of 5 and a standard deviation of 2. And you can see it spits out 100 numbers just like that, and they are labeled. You can assign these to a variable if you feel like it, or in many times you won't even have to input your data, and you can use the PDF function, dnorm. And let's again use a mean of 5 and 2, and we'll say, let's find the probability that in a distribution with a mean of 5 and a standard deviation of 2, what's the probability that a value of 3 occurs? So that would be dnorm 3, 5, 2. And we can see that that probability is 0.12, which is about roughly 12%. Now the CDF, using the pnorm, takes these same inputs and finds the probability that the random variable x is less than or equal to 3 when it has a mean of 5 and a standard deviation of 2. And we can see that value is equal to just over 15%, or 0.158. The next distribution we'll cover is the exponential distribution. A random variable that follows an exponential distribution is described by a parameter lambda, where the PDF is shown here, where the random variable x has a parameter lambda. The PDF is equal to the exponential variable raised to the negative lambda power multiplied by lambda to the x power, all over x factorial. And lambda is often a rate per unit time or area. You'll remember that from the Poisson distribution for discrete random variables. And the CDF can be seen below, where it is, you can see the PDF integrated for when x is greater than or equal to 0, and 0 otherwise. The formulas for expected value and variance become simpler, as you can see here. The exponential distribution is often used to model times between events occurring, which is closely related to the Poisson distribution, but it's important to recognize the difference between the two. The Poisson distribution marks the rate of events happening, a discrete distribution where you're counting events occurring. The exponential distribution is a continuous distribution and marks the time between those events occurring, which, as a measurement, is a continuous random variable. The last distribution we'll look at in this video is the uniform distribution, where the PDF of the random variable is represented by this equation. For any value between a and b, the value of the random variable x is the same, 1 over b minus a. This distribution is deceptively simple and can often be overlooked in a problem statement. Most times in your homework problems or on tests, the distribution will either be stated or you will be able to recognize the population parameters. If it's a rate, if it's lambda, it's going to be an exponential distribution. If it says uniform, use uniform. It's very important to recognize what the problem statement is telling you about the distribution for your random variable. The information in this video can be found in Chapter 4 of your textbook, Probability and Statistics for Engineering and the Sciences, by J. DeVore.